Just unplug for 1 second. So I can put it here. Try it. Lean down.
So we're supposed to show up at 1:30 for the place. That's right. Traditional path.
Yeah, off Wednesday. Yes.
Is that better?
Yes.
Let me get those two.
Can you see it? You can see it okay? Is this better or worse? Makes no difference. Worse. Ready?
Let's do it.
All right, welcome everyone to the AI and Math seminar. This is our first seminar of the semester. There's many more to come. I hope to see as many people as we have today every week. To kick things off, we have a talk by our very own Alex Kontorovich, who's going to give us a little introduction to what we've been doing for the past few years and what his unique point of view on lean and mathematics and AI is going to be. So take it away.
Thanks, Ian. I'm not sure how unique it is, but we'll do it anyway. So my goal is just to show you how you could get started with this stuff if you know nothing about lean, although I will cheat a little bit. So what I should be, if I really wanted to do this completely web-based, then I could, but there are so many people using this server. There's a server that just runs lean that it might break, and so I have a backup if it does. But otherwise, we're gonna just play an experiment. So throw out your favorite piece of mathematics, and let's see if there's a way to formalize it. The Pythagorean theorem. Okay, so tell me about the Pythagorean theorem. I asked Claude. I didn't even finish the M, but it'll figure it out. Can you see that? Should I make it a little bigger? You see it in the back? A little bigger? How's that? Okay. And then you presumably want something like a proof. Give me a proof in natural language, but in a style that I'll later be able to formalize in lean. Okay, so I'm just talking to this is Claude AI. Is that better?
I think just the lights off the thing.
Yeah, I couldn't get. Yeah. If we put them too far down, then it's nap time.
No, that's good.
For me. That's good. Okay, so of course the AI can talk like this. We all have seen this. It just talks and says, yeah, I can tell you the proof. Here it is. Why this will work for lean, basic algebra. Okay. Then I'm going to say, see, the Pythagorean theorem already is in the library. And so it's not a great example because what should happen right now is I'll say, what's a good way to, let's try it. What's a good way to formalize this using anything available in MATLib4? Look it up. Okay, so the look it up is tell it to use RAG. RAG is retrieval augmented generation. So it's doing a Google search for what the latest library. Does everybody know what I mean by lean and MATLib? Should I define these terms? I think maybe most people know, but just in case, lean is software that helps you formally prove theorems, and MATLib is the library built on top of lean that contains lots and lots of theorems that people have proved. And so it's still looking, it's doing multiple Google searches. I'm not sure they're really Google searches. It could be some kind of internal search that its system is in a controlled environment allowed to do, so it doesn't land on some website with, bad code or something. Okay, I found the relevant information, and perfect, I found what we're looking for. MATLib has something called an inner product space, and there's a theorem called norm add sq, which is norm add squared, which says this, and it gives me the link to it. This is the key result we'll want to use. Okay, so let me just click on this and see what it says. It does take me to the page. Can you see that? So this is some web page in MATLib under analysis in the subsection about inner product spaces, and these are probably the basic definitions. And then, the main results is, well, a Cauchy-Schwarz inequality. That's good. How about even simpler than that? Before we get to Cauchy-Schwarz, we should have the Pythagorean theorem. And Claude seems to tell me that it's called norm add squared. So let me find norm add squared, which is right here. And, well, this is the Pythagorean theorem, except there's a cross term. I'm not assuming that x and y, it's better than the Pythagorean theorem. It's the cosine formula. So what if how about the special case when this inner product is actually 0? Yeah, it even says, here it is. So this is the key result I'll want to use. And then it suggests the formalization. So let's just take what it said and see if it has a chance to work. So I'm going to just copy this. I guess I could put it in here. Let's see. Yeah, the server has stopped. Okay, let's not mess around with the server. I have a version of a local version of lean running. Can I make this a little bit bigger? Now, the first thing it's going to do is it's going to import something, and 9 times out of 10, it gets the import wrong. In this case, I think the import's okay. So there's no harm in importing all of MATLib. And let me slide this over just a little bit. Okay, so it made up this symbol that doesn't exist. Can I just do that? Well, wait. Let me not use my knowledge of things. I'll just tell it. I'll just tell Claude that what it told me is not quite correct, because I don't know what this underscore thing is. So we could also there's also something called MATLib geometry Euclidean projection, which has a theorem called dist orthogonal projection square add dist orthogonal projection. That is kind of right for a MATLib name. So let me just grab this and see what it is in the library. So here's another copy of the documentation. Indeed, it actually exists. This is the distance from P1 to P2 times the distance from P1 to P2. Okay, so that's distance squared is equal to the distance between P and the orthogonal. This is all too complicated. This should just be the Pythagorean theorem. So let's before we do too much more, no, this is all too complicated. There should just be the Pythagorean theorem already. We'll leave the Pythagorean theorem very, very soon. I think there are other examples that are more illustrative. You're absolutely right. Let me search for the actual Pythagorean theorem instead of giving you all this other stuff that will imply the Pythagorean theorem, Lisa. I'm using Claude because I've tried Gemini and I've tried GTP and I've tried Grok. And well, first of all, it's the one that I pay the $20 a month to. And so I have, I've been using it for 5 hours already today, and I still have tokens. It's not kicking me off the system yet. I find that for formalization, for some reason, it's better at coding, in my experience so far. I haven't played that much with GPT-5, so it might be just as good, if not better, but this really solves so many of my problems that I spend a little bit of time, like a couple hours every month, trying out the other systems. And by now, I just know how to talk to this in ways that I don't know how to talk to GPT or Gemini. Okay, you're right. I've been overcomplicating things. The Pythagorean theorem, again, it's using this symbol that it's not going to recognize, but it's what's the name? Yeah, I don't want to apply. I'll ask it one more question. I don't want to apply a theorem. I just want to quote it. I just want to quote it. What is the name of the Pythagorean theorem in MATLib? And again, typos, errors, it's very good. I don't bother to delete my bumbly fingers. Give me the exact name. I'm not even going to bother doing a Google search for it. We can compare, actually. Let me not even bother. Okay, so yeah, that's the kind of thing that I think would be in there. I found it. Nope, that's still not the one. Okay, so this is the kind of thing that happens, and we wound up in some vector in this language model, and it's not a good vector. And what I would often do is just start a new tab and run it again. Let's see if it's not going to be called Pythagorean. Well, Pythagorean triple, I was going to say, but Pythagorean theorem is not going to work. Okay, fine. Let's do a Google search. So Pythagorean theorem in MATLib 4, not 43. Yeah, see, I no longer do Google searches. Okay, here we go. 100 theorems. I mean, this is not the page that we're supposed to be getting, but there it is. It's an if and only if, and where's the documentation for it? So here it is. Yeah, okay. Yeah, this is the Pythagorean theorem, if and only if. So this is in MATLib geometry Euclidean angle. There's a whole subsection on angles, unoriented angles, and right angle. And that's the file. And what it says is if you have 3 points in a metric space that's also an inner product space, and normed add torsor between V and P, where the metric space is, you have to click through these things. And you can click through these things if you want to know what each of them means in various contexts. You have 3 points, P1, P2, P3, and distance from P1, P2, P2, between P1 and P3 squared is equal to the distance between P1 and P2 plus the distance between P2 and P3, if and only if the angle between P1, P2, P3 is pi over 2. Okay, so it's the Pythagorean theorem in both directions. I-47 and I-48 in Euclid Book 1. Whatever. Okay, something else. Yeah.
Just to riff on that.
Yes, please.
For example, you and I know what a Banach space is. If you look up if you try to find a Banach space in here, it's,
Okay,
you know, it's a compilation of objects,
yeah,
right? Then,
normed add vector space, yeah.
so it kind of requires you to understand kind of all the components of a Banach space, right? Whereas I think when you say, oh, I'm using a Banach space, you're not in the back of your mind keeping track of all the properties because you've already digested what a Banach space is, right?
Yeah.
So is there a way to just look up Banach space without keeping track of all the pieces that it gets built out of? Do you understand what I'm asking?
I do. Let's see what Claude comes up with. How are Banach spaces formalized in MATLib 4? I probably don't have to put the 4 anymore. There was a period of transition from 3 to 4, and it still hasn't. Yeah, it's easy enough to put the 4 there. Okay, so I need the Banach space is formalized as a normed vector space that's complete with respect to the metric. Okay, the type class is normed add group and normed space. The completeness is class complete space. So a Banach space over a field, typically the reals or the complexes, is you add these three things. Now, you could just say, okay, so what's something you would want to do in Banach spaces?
I'm thinking of contraction mapping, for example.
Okay,
So how good is this, the result of this search?
it's
Is
pretty
this
good.
accurate?
It's pretty good. Yeah, give me a sample theorem using Banach spaces that I can check in Lean. Let's see if it'll give us something. The point of this exercise is just that you can play with these things. You just talk to them in natural language. They spit things out, and I would never trust what it spits out. I would take what it spits out. Okay. I'm going to copy this, and I'm going to put it into my sort of dummy thing. It doesn't, this isn't the right file. I probably have to refresh the server dependencies. And then, so what's A? A is a metric space. It's a complete space. It's non-empty. I need more conditions than that for it to be a Banach space. And then I have a function f on the space and a constant k that's less than 1, a real number. Presumably I want it to be positive, but okay. With the property that for all x and y, the distance between f of x and f of y is less than k times the distance between x and y. Is this thing like jumping every 5 seconds? It's, I don't know what.
But this is because this is the topological version of the contraction mapping theorem. You don't need the Banach structure.
Right.
And it was smart in that sense, right?
Well, I just said, give me some sample theorem that uses Banach spaces, and it
Gave up on the Banach.
It gave up on the Banach spaces. Here's something a little bit better. Okay. Let's try this one. So I'm just going to ignore all of this and try something else. Okay, so it compiled the statement of the theorem, but not the proof. So before we go on with the proof, let's look at what it's like to work in Lean. Okay, so example means we're going to prove a theorem, but we're not going to give the theorem a name because we're never going to use it again. So it's just a way of saying theorem, no name. So that's an example. We have three things called K, E, and F. We're going to explain what they are in a second. K is a non-trivially normed field, so complex numbers or something. We have a normed, better be the real numbers. Normed additive commutative group E. So it's an additive commutative group, and it's a space over the reals, and it's complete. So E is a Banach space, and F is a Banach space, and little f is a linear map, linear over the field of the reals from E to F, and it's surjective. And the claim is then that map is open. And Lean accepts all of this information. What you're seeing on the right-hand side is I'm starting the proof here, and sorry means I don't know how to prove it yet. And this is what Lean currently understands, and it currently understands everything that we just told it to put into its working memory. That's not even the one that's, if I step on this, it shouldn't affect the HDMI. Okay. We have K, E, and F as before. We have these instances. We're just assuming that K is a non-trivially normed field, that E is a normed additive group, yada, yada, everything that we just read. F is this function. We have this hypothesis that's called HF, that the function F is surjective. Now, this funny up arrow is that surjectivity is a property of functions. And F is more than a function. It's a function together with a proof of the linearity over K. So we want to forget that linearity over K and just think of F as a function, and that's what that up arrow is reminding you of. That it is an extra structure that we're dropping. And then we want to prove that this F, which again has this extra structure, when we drop that extra structure, gives us an open map. Okay, let's just do one little move before we do anything to see why, how you could get started. So I don't know what it means to be an open map. Let's pretend. So I will unfold this definition. So remind me what it means to be an is open map. How does Lean actually handle is open map? So the way it handles is open map is that for every set of the domain, if U is open, then the image of little f under U is also open as a subset of the target. Okay.
different from hovering the cursor on the thing on to some folks.
Very good. So before I unfold, and the beautiful thing is everything is all of the game, I call these game boards. Because I think of this as giving like instructions, like in a chess game. This is E4, and the next one is, two ... F knight F3 or something. So these are the instructions. And then at every point in the game, you can put your cursor there and it'll show you what the game board actually looks like at that instant. And so your question was, so if I put my cursor back to line 8 before we did the unfolding, it changes the game board back to the original version. And then if I hover over what is open map is, it's just a property. It's not going to unfold it all the way down to the definition. So that's what this is open map thing is. It's a function that takes a map and returns true or false. Yes, it is open, or no, it's not open, based on whether this condition is satisfied. The condition being, given any open set, if it's open, then the image is also open. Okay.
Thank you.
So then how did you start a proof like this? So now, this is what we teach our students. Well, remember what. Okay, there we go. Remember what it means to be open. It's that for any open set in the domain, the image is open. So how do you start a proof? Give me an open set. Yeah. So introduce an open set. Intro U. Intro U means give me that open set. So now the game board has changed. The game board from when we first started, this was, we shook hands, and then won E4. The first move was made, and the first move was just to unfold the definition. The second move is now we have a new hypothesis. The new hypothesis is that we have a set in E, a subset of E. And then the new goal state has also changed. The new goal state is if E is open, then the image under F is open.
What is this notation there? Arrow F double O?
This,
Yeah.
So this notation, let me make it look slightly nicer. Okay, so in mathematics, we abuse notation. We write F of X when X is an element so if X is in our target space, we write F of X, and that will be, so if F is from U to V, then if X is here, then this will be an element of V. And then if we have or maybe this is our total space, E, we had E to F. Okay, so X is in E, and then this was F. But then if I want to say, what about F of U? That's an abusive notation. F is supposed to actually take elements of E, not sets of E. And so the lean way of doing it is to do that. So you're not abusing notation. It wants to see explicitly that you've changed, if you have a map like this, then you have a map like this from subsets of E to subsets of F. And so that's what this it's the image under F of the entire set. And then, so if U is open, then the image under F of U is also open. So what should we do now? So we said before we unfolded, or actually after we unfolded, it was for any open set, if it's open, then its image is open. So we said, okay, give me a set. And now the claim is, if that set is open, then the image is open. So what should we do? Well, assume that it's open, right? First, we should, give me a U and make the assumption that it's open. If it's not open, there's nothing to prove. How do you make the assumption that it's open? So it's again intro, because it's give me an arbitrary set U and then give me the fact, let's call this a hypothesis on U, HU, which is the hypothesis that U is open. And now the game board has changed yet again. Now the game board says we have a set E, and we have a hypothesis that U is indeed open.
And Lean just knew that was the natural thing to do.
Well, it knows that there's an implication, P implies Q, and it knows that if you want to prove P implies Q, and you say, well, then give me P, introduce P, then it should change the goal state from the game board from, whatever, and then P implies Q to whatever, and P as an assumption, and the goal changes to Q. It knows modus ponens.
If there were, can't off the top of my head, but I could imagine there would be multiple possibilities of what should be introduced, right? If you had,
It's just in order. So if your goal, this is a turnstile. If you want to get out of, it's an escape room. You want to escape, you got to cross the
so it's
turnstile.
just gonna go
So-
through the list of.
Yeah, if you have P implies Q implies R, if P, then Q, then R. So if you intro P, then you get the first thing, and that the goal becomes Q implies R. You can intro, in fact, secretly, I mean, this is secretly, you're trying to create a function from sets of R to proofs that those sets are open to proofs that their images are open. And so we could have done this in one fell swoop. We could have introduced both U and HU in the same line. And it'll just immediately unfold everything that you want unfolded. Okay, now we have to prove that this is open. And well, I don't know how to prove that it's open. So maybe what's the definition of open? So unfold is open. And well, that doesn't help because the way it's open is that it's open as a topological space. Well, and that won't help either because the way that it's open as a topological space, well, it's just there's a topological space is a collection of subsets that are declared to be open. So maybe this unfolding wasn't so useful. Let's just grab the entire game board and give it to Claude. Help me make progress on this goal state. I just dumped the whole thing. It's not nicely, there's no, I didn't like make a new line. I'm just dumping text and hitting go. We need to show that F maps open sets to open sets. You have that F is surjective. You can use the open mapping theorem. Here's how to proceed. Okay, it says just quote the open mapping theorem. Fine, I'll try it, but it didn't work last time, so I don't think it's going to work this time either. So what this says is, what it's trying to do is, it thinks there's something called is open map of surjective that takes a function and takes a proof that that function is surjective, because that's what HF means, and proves the openness, meaning if we have a U and we have the fact that U is open, then that's exactly the statement that we want. The problem is the environment does not, it made up the name of a function that doesn't exist. It made up this name is open map of surjective. The environment doesn't contain it. Okay, so all I'm going to do is let's grab this error message and feed it back into Claude. I don't think that name is right. Can you look up the correct name? Here's the error message. I just pasted in the error message. Let me search. So it's going to do another rag, and maybe it'll find it. So what it was looking for is continuous. It thinks F is a continuous linear map. That's what this arrow with an L, it's a linear map over the reals. And there's no such thing as is open of surjective. I can see that there's a theorem called quotient map. Okay, I'm not sure we're not taking quotients. Okay, it's just called is open map. Let's see if that's right. So it's a little annoying that you have to tab things over. And okay, so what happened? So I just copied what it said and pasted it in. There's apparently a theorem that it just got the name wrong. It looked up the theorem. When I hover over the theorem, because it's a theorem and not a definition, you'll actually see what the entire theorem is. So I just hovered over the theorem. Let's read what the theorem says. It's called continuous linear map dot is open map. It takes some K and K prime. They're both non-trivially normed fields. I'm thinking of real numbers. Sigma is some, so it's a function that preserves addition and multiplication, also a ring operation. E, so let's work backwards. Where's our little f? Little f is a function from E to F that's linear. I don't even know what SL. Oh, SL, right. It's linear. It's like skew linear with respect to whatever this sigma is. In our case, it'll figure out that K is equal to K prime and sigma is trivial. And so this just boils down to being linear. And These are ring Hom invariant pairs, sigma and sigma prime. So there's a map from K to K prime. There's also a map from K prime to K. All of this stuff is going to be worked out under the hood. You don't have to give any of this explicitly. Lean will figure out how to apply it in the situation. And the only thing we need to know, the only thing that we need to know is what is the function and the surjectivity. Surjectivity, that's just the name of the hypothesis. And the hypothesis is F is surjective. And again, it's not F, but the F when you drop. Is this what it is? I'm not going to touch it because it's not broke. Okay, does that make sense? Then we get that F is an open map. And so if we apply this theorem, at the end of the application, what's left to prove is that the set U itself is open. But we already have that as one of the assumptions. So the way to get past the turnstile is exactly HU. So that's this exact HU. And now it's complaining because I said sorry. It says there's nothing to apologize for. There's no more goals. You finished the there's no goals to be solved. So get rid of the sorry because we're done. Okay, so we proved a theorem. We didn't really prove a theorem. We kind of interacted with Claude to look up the theorem and got a little bit of experience of how to do it and found this theorem called continuous linear map dot is open map. So if we're not doing any mathematics today. So if you didn't know before that when you have a surjective map between two Banach spaces, it's automatically open, now you do. Good. And the library knows it and can find it.
Can you produce a data output which produce a natural language output where we can use the proof?
Very good. Okay, so let's, this is the theorem that we really want. So can you give me a natural language proof of this? Continuous linear map is open map. That's a much easier thing. It's read that in 100 textbooks. That Banach spaces.
It's follow from this formal proof, right? So now you have a formal proof of the theorem.
Yes.
I like to read it as a formal proof.
Okay. Very good. So let's try to actually look at how the theorem is proved in the library and see if we can make sense of the proof. In fact, a good way to do that is I can right click on this and go to definition and it'll skip me right to where it's proved. Okay, so here's the proof. All right, you asked for it. So we have this even more general setup where the fields, don't have to be the same field as long as there's some map between some ring homomorphism in both directions. Together with the fact that it's a ring hom invariance pair. That's like an assumption going on. Okay, we have to prove that it's open. Now I'm looking in the library. And look at what the first line of the code is, intro SHS. What is that going to do? We know what it means for a map to be open. You give me a set and you give me the fact that it's open, and it's exactly what we did. It was our first step of the proof. So when I click on that, you can see here, we added a set. They called it S, I called it U, and the hypothesis that it's open, and now we have to prove that it's open. Okay, well, there's a theorem called exist preimage norm LE. We can fix the clock pretty easily. I don't know how easily we're going to be able to fix this. It'll be pretty bad if all semester long we're fighting with the HDMI cable.
Screen a little higher.
The problem is that the plug is not.
We'll try to talk to and see if we can get this fixed.
The plug is kind of broken. The socket there is not holding.
It's barely, it's like hanging down, and I don't even want to touch it because I'm very careful not to step on that. Okay, so, I mean, okay, let's see, instead of trying to read it ourselves, let's see if we can ask the AI what's going on. So I'm just going to copy this proof, and you see it's a real proof. I mean, there's something to calculate. So it's applying some theorems. It's claiming that f of x plus w is equal to z, whatever x and w are. And then we say that x plus w is in a ball of radius epsilon about x. And why is that true? Well, we have to do a calculation that the distance between x plus w and x is w. And then that's less than or equal to this constant times z minus y. And the distance between z minus y was assumed to be at most epsilon over c. And then we're done. But let's say we didn't know how to read that. So I'm just going to copy this whole thing. And give it to Claude. Where were we? I'm just going to start a new Claude. Oops, not chess, Claude. Give me a natural language translation of this proof in Mathlib 4. Paste. Gathering my thoughts. Good. You should gather your thoughts. It's probably talking internally to itself and doesn't want to show you what it's saying. You know, think really hard. This guy's giving you a hard problem and wants a good solution. Okay, so here's the theorem. If F is a linear map and it's surjective, then it's an open map. Let S be an open set. We need to show that the image of F under S is open by the open mapping theorem machinery, since F is, well, I mean, that's begging the question because that's what we're trying to prove, but okay. Somewhere else, we've already proved that there exists a constant C, so that every vector V, we can find a pre-image whose norm is at most C times V. Okay. And then we show, to show that it's open, we verify the condition at every point, that every point has an open ball around it contained in F. So now give a point, give me a point in the image. Then there's, okay, some pre-image points, so some X, so that happens. Since S is open, there's an epsilon ball around X. Okay, so it's really just doing, you can sort of follow this proof line by line, and then you'll see that it's doing exactly the calculation that was.
So we can come in competition. You may have a,
Well, I don't know who would publish.
I mean, it's a known theory. I
Yeah.
mean, suppose you have a formal proof. and-
If you have a formal proof, the translation from the informalization is a much easier problem than formalization. The hard thing is taking what we know as natural language and converting it into a formal proof. If you already have the formal proof, you know, I mean, as you saw, you don't even need to, I mean, once you get used to reading these kinds of things, you will just see this and see this. Okay?
There's no guarantee, though, that what it told you is actually.
That's right. That's right. I would have to, you know, if I didn't know this subject, I'd have to sit there, slowly go through the details and make sure that it's doing what I think it's supposed to be doing. Constantine.
Can I go back to my original question?
Yes, please.
So let's go back to the bottom, the lean statement. I guess further down, I mean, there's all the stuff that's in the hypothesis further up. So
Further up. You mean from the beginning here?
from the beginning, we have all the statement of what a Banach space is.
Yeah. Okay. So even farther back, just to our little example.
And yes, that, the set of conditions that is put down has given us Banach space.
Yes.
But I'm thinking pedagogically, right? Our students. Right?
Yes.
We teach students about Banach spaces. We don't teach them about non-trivially in one field and
Yeah.
commutative groups and
So you would like there to be just a thing that says, forget about K. You just want to say Banach space over the reals E. And it's very easy to add that to as a class. Let's see if Claude can do it. I want to be able to say this at the top of my lean file and have it just extend the standard conditions for being a Banach space. It's really frustrating, I'm sorry. How do I set up the structure? How do I set up the structure, or actually class, or the type class? Okay. So I'm just going to copy that. I don't think I grabbed it. Here we go. And I'll copy it here. And now let me just exit out everything else that's going on so that we don't see it. Not my Banach space, just Banach space. Banach space. Oh, example. No, variable. Variable. Variable E. This just says, okay, I'm not able to synthesize. Okay, so I need to tell it explicitly that it's a normed additive group. This isn't great. Okay. Aha. Let's extend one more thing. Let's change the extension one more thing. Maybe I need to do them in this order. There we go. Okay, done. So if you wanted to tell the library, let me just get rid of everything else we've done so far. If you want to just tell the library, let's see, can I make this look a little nicer? There we go. So you are welcome to propose to MathLib, to the library, a definition called Banach space, where you give me whatever the underlying field is, reals, complexes, and a number E, a letter E for what you want to call your space. It will package, it will need a proof that K is a non-trivially normed field. The square brackets means it's something Lean should be able to figure out in context. So if I give it the real numbers, it already has that theorem. You shouldn't have to specify. It'll go find it. If I give it the complex number. The real numbers. Extends, it's going to assume these three things, and then I don't have to say anything else. So for whatever reason, the makers of the library have decided that they just want you to be specific and add those three things, instead of being able to say, I have E, I want it to be a Banach space over reals. So that's a decision that's made within MathLib. You're welcome to go on Zulip and say, hey, I would really like to be able to just say, let E be a Banach space, and this is how I would say it.
So, I mean, because I know you're teaching real analysis with this. So
Yes.
are you using these kinds of things in your class?
The way I'm teaching real analysis is a much more controlled environment where it's purely web-based. I mean, yeah, all right, let me take 5 minutes and just show you what that looks like. So there's a website that's being run by a server somewhere. And, you know, there's lecture 1 and lecture 2 and problem set 1 and problem set 2. I'll show you what the last lecture was. So the last lecture, we proved the uniqueness of limits. And here's the uniqueness of limits. So our objects are a sequence, A, which is a map from the naturals to the reals. That's what a sequence is. And two real numbers, L and M. We assume that seq lim A, L, in other words, A goes to L. There should be better pretty printing for this and sugar, syntactic sugar for this. This is still a work in progress. But anyway, if you don't know what seq lim is, you go over here and say, can you remind me the definition of seq lim? And it says, oh yeah, that for all epsilon, there exists an n, so that for all n greater than capital N, a n minus L is less than epsilon. So it knows what that is. You can remind yourself what tactics you have access to. You can remind yourself what theorems you have access to. And you get more and more, you get access to more and more theorems as you get farther into the game. And so our objects are a sequence, two real numbers, L and M, the assumption that A goes to L, the assumption that A goes to M, and your goal, the turnstile, is to prove that L is equal to M. And so the suggested proof, I mean, there's some discussion here about what it's going to be a proof by contradiction. That's the only way you can get started. So assume, so you're supposed to learn this by contra thing. So I say by contra H, and the goal has changed. And here I'm keeping track of, I'm showing you every single board. So our original board was here. This was the command, and now this is the new board. The new board is our goal changed to contradiction, trying to prove false. And we added one more hypothesis that I called H. I just gave it that name, could have been anything. And that hypothesis is that it's not true that L and M are equal. And given that, how are you supposed to make your way towards the contradiction? And so that's, you know, this is just, what I really do is we go over it like on the board or on paper, we go over what that proof is, and then we check that we've actually proved it by putting it into the game and seeing that we've done everything we claimed we would do.
Yeah, okay, no, it's the controlled part.
This is a much more controlled environment because, well, for a variety of reasons, but one of them is that I don't want to have to teach people how to set this up. And I can't rely on the lean server when there's,
Not only that, but I mean, that's what we call the Bonnet space, right? I mean, there's so many, you know, it's done on the level of abstraction.
sure, but I can very easily set this up, in the case of real analysis, at least. I can just immediately start typing things like, what does it mean for a sequence to converge? It's that for all epsilon positive, there exists an n, so that for all n greater than or equal to little n, the absolute value of an minus L is less than epsilon. Okay, so that's the definition. And then let's prove a theorem. How about the constant sequence? I'll just give it that name. So A is a sequence from the natural numbers to the reals. And I have a real number L. And I have a hypothesis, let's call it HA, that for all n, A of n is actually equal to L. And then what I want to prove, I want to prove that seq-lim AL. Okay, should we go through this? This will take about 10 seconds. And I think it'll be pretty illustrative of what these kinds of things look like. So the first thing we might want to do is remember what the definition of sequential limit is. So let me unfold the definition. And it changed the game board. Trivially, it just put in what the definition was. We rewrote the definition one line ago. And so for all epsilon, that means give me an epsilon. So introduce the epsilon, introduce the fact that epsilon is positive. So now we have two new things in the game board. We have an epsilon, and we have that epsilon's positive. I want to show that there exists some n. So now you have to think, how large an n do I have to take? How large an n do I have to take so that eventually an minus L will always be less than epsilon, any value, because it's the constant sequence. Let me pull this over just a little bit so it looks a little nicer. There we go. Okay, so what value of n should I use? 42. Okay, and so now the goal is for any little n, at least 42, I want to have this inequality. So give me little n and give me the fact that it's at least 42. So intro, little n, and a hypothesis on little n. Now I have two new things. I have a natural number n, and I have the fact that it's at least 42. Because I have this natural number n, I can specialize the hypothesis, which is true for all n. I'll specialize it to this little n. So specialize, what was that hypothesis called? HA, to the value little n. And now HA says, not only is it true for all n, it's true for this n, that A of n is equal to L. And so let's rewrite that condition into the goal. So let's rewrite HA. And now it has replaced, and it even tells you what it replaced. It replaced the A of n by L. Let's simplify. So when we simplified, L minus L turned into 0, the absolute value of 0 turned into 0. And now I have to prove that 0 is greater than epsilon, but I already have that. That's exactly this. So it's exact H epsilon. Exact, whoops, H epsilon. It's almost like I know lean syntax. And then, sorry, there's nothing to be sorry about. The goals are done. We proved the theorem. There's no goals. That's what it feels like to prove theorems formally in real analysis.
So because every proof's going to be constructed, do you have to put in a value of n?
Yes. Well, what value do you want? So you're at this point, again, to stay with the escape the room example. You're here, and you will not escape the room until you make progress on this goal. And the next thing it wants is a value of n.
What if you did a variable n in natural numbers and used that and made your way through it?
So in other words, you want me to make a global value of n. So variable. Yep. So that means I globally have hanging around. It won't appear until I actually invoke it. But
And you can't do that inside the proof, just introduce an arbitrary natural number.
You cannot introduce an arbitrary natural number because you have to say what you want that natural number to be.
And so now if instead of use 42, you use capital N?
Yeah, exactly. I think I should be able to use capital N. Let's find out. No, it doesn't know it. It doesn't know it because I put it in square brackets. What if I put it in curly brackets? Then will it know it? No. Yeah, I guess having it as a variable on the outside, that's supposed to make a global variable, but this theorem has never called it. But if I just give myself a natural number somewhere, so now I'm saying, suppose I have some natural number floating around somewhere, then certainly I can use it and the whole thing goes through. But I shouldn't have to prove this theorem with a natural number. The point really is that in natural language, at this point, you're supposed to specify how far out you have to go. And of course, you can go to 0, you can go nowhere. You can go to, right? I can use 0 and the proof will still be just fine. But yes, you do have to, I don't see this as a constructive versus not constructive. We have proofs by contradiction. We have proofs by all kinds of non-constructive processes. Yeah. That's not the issue. It's that I have to specify a natural number and I don't have any natural numbers. I don't have a single one floating around.
So in this, this looks very much like the way a mathematician would prove.
That's the idea.
So there doesn't seem to be any type theory in this.
None. I'm teaching 0 type theory. They ask the questions about type theory and I say, no, that's a type theory question. I'm not going to answer that.
So are you walking inside part of MathLab that uses CFC?
No, this is all based on dependent type theory,
It's all,
but it's all hidden under the hood. There's a couple of places where you start feeling it, actually, when it's the casting. Casting becomes, some of these levels are about casting and they're very annoying and I wish they didn't have to exist. And there should be better ways of handling it. Let's see. Is this a good one to talk about casting? No, that's too easy. How about the algebraic limit theorem? No, that's too easy. Maybe lecture 3. Yeah, lecture 3. Okay, here we go. So the Archimedean property. There's a whole discussion here about the Archimedean property. So the Archimedean property says you have a real number, epsilon, and no matter how small it is, I can find a natural number. I mean, I would think about it the other way around, that 1 over n is less than epsilon. But if you put 1 over n is less than epsilon, that is a trivial proof. You said n equal to 0, and 1 over 0 is 0, because in formalization, all functions are total. They have to take values on all inputs. And there's a junk value given to division by 0, namely 0. And so that's the wrong way to prove this theorem, or to even state this theorem. So it's the wrong statement. It won't be usable in practice. But the way I do it here is that 1 over epsilon is greater than n. And now you start seeing the difference between type theory and set theory. Is that n, I mean, this really, I'm postponing the discussion of what the real numbers actually are. We're using the real numbers and proving things about them. And I keep pointing to the fact that we don't know what they are and we're going to later need to learn what they are. But this up arrow is the first hint that there's something going on. And what's going on is that n is actually a natural number. But it's being compared to a real number, and there's no comparison. You can only compare the same kinds of things, the same types. And so you first have to take n and cast it into an integer. And the casting into an integer is, integers are pairs of natural numbers. One way of thinking about integers is they're pairs of natural numbers with an equivalence. So there are pens here. I'm going to write on the whiteboard in a pen. I don't know who put that there.
so is the up arrow an injective function?
The up arrow is a coercion, exactly. It's an injective function. Yeah, so let me not write anything. Real numbers are in Lean are implemented as equivalence classes of Cauchy sequences. So I need a Cauchy sequence, and that Cauchy sequence in the case of n is n, 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 n. So this is hiding the fact that what you're going to do is take the sequence of all n's, prove that it's Cauchy, and then take the equivalence class of all other sequence equivalent to that, and that is the real number that this represents. So that entire construction is being hidden by a little up arrow, but the up arrow is there to remind you that something is happening. So you do see, but I wouldn't even call that dependent type theory. I would call that mathematics, because we make a whole big deal about the construction of the real numbers, and then you start comparing things that are natural numbers that just come from 0 and the successors of 0 and successors of other natural numbers. And then you want to talk about reals. You should actually take that number, convert it into a real number, and then you can compare reals and reals. And this is doing it for real, as opposed, in actuality, sorry, as opposed to what we usually do, which is just, we think of the naturals as a subset of the reals. There's an injective function, but it's not a subset.
So
So-
we have to change the way we do set theory. as well.
If you like, yeah, or just don't base the foundation. You know, I remember I took freshman spring, I took set theory and found logic and foundations with Conway. He made like this whole big deal about everything is a set, you know, you have to define things from scratch. Here's DFC, here's how you do everything. Functions, how do you define a function? A function is a set. You take the product function, you take the graph, yada yada. And then next semester, I'm taking like algebraic topology or something. And lecture 1 is, okay, so let's look at the space of continuous functions between these two topological spaces. Like an idiot, I raise my hand. Excuse me, professor, how do we construct this from Zermelo-Frankel? It's like, get out. I'm actually trying to do something, right? That's not what we do. We give lip service to foundations, and then we just do math. And dependent type theory actually allows you to just do math. In dependent type theory, the function is the primal thing, not the set. And so if you think about how hard it is to make a function out of a set, you have to do that whole graph construction, as opposed to how easy it is to make a set out of a function. What set E is actually functions from E to prime. Just, is this point in the set or not? That's it. So it's trivial to make sets out of functions and much harder to make functions out of sets. And in natural modern mathematics, functions are way, way, way more important than sets. And so the early type theory, the early formalization systems were based on set theory as their foundations, and they were able to formalize very, very few things in modern mathematics. And when they switched over to type theory, it just went.
And so that's a higher type, the function is a higher type than.
You mean
Types.
higher type in the sense of universes, in the hierarchy of universes? So I don't think the function is a higher type. Maybe it's a sort 1 instead of a sort 0. Yeah, it's only when you get to like Teichmuller spaces kind of construction that you actually get higher universes, where you're trying to avoid Russell paradox. Like a Teichmuller space is an algebraic variety whose points are themselves algebraic varieties. And now you have this issue of, you know, subsets of themselves and this kind of nonsense. So that's why the way Russell got around this when he invented type theory was that you have this hierarchy of universes. And so if the varieties that are in universe U, then the Teichmuller space containing those varieties, which is itself an algebraic variety, has type U plus, is a type of universe U plus 1. That kind of thing. So you can't even, there's no sense in saying, is it a subset of itself? That doesn't exist. So you're right. That's the kind of thing that this construction avoids. But I don't talk about any of that when I'm teaching real analysis. They don't need to know. I've told them, I mean, they see the up arrow and there's something funny about the real numbers. We haven't constructed them. When we go to construct them, they'll see that what this is doing is it's really, really, it's not just paying lip service. It is actually going down to the foundations every single time you call a natural number in a context where it's supposed to be compared to a real number. It's constructing an equivalence class of Cauchy sequences of the constant sequence n, which is what we said we're supposed to be doing, but we don't do that in natural language. It would be insane. And you don't have to do it in formal language. It'll do it for you. But you just have to know that that's what it's doing. Anyway, I think that's close enough. So let me stop there. Thanks.
Is there an efficient way to avoid the portion of Mathlab 3 when you're getting the answer from AI?
Just put a 4 at the end of your question. Yeah.
I tried that.
It's still giving you, I mean, everything it's been giving me so far has been lean 4.
Right. But when I was trying to put something more complicated,
It was still
come
giving
up with like weird theorems and tactics.
As you saw, it already was hallucinating
Yeah.
names. So it hallucinates